This week we'll begin with our own postdoc, Mehta, who will talk about higher dimensional Bosonisation.
Right. All right, thanks. And yeah, thanks for inviting me to give this lecture in Boulder Summer School. This will put down an entire slide full of notation over here. Unless we get to the actual technical gory stuff, we won't be using most of this. So please don't feel afraid by the 1, 2, 3, 4, 5, 7 different types of brackets here. Most likely I won't be getting to any of those. This is just there for completeness in case I do. So this entire lecture is mainly going to be about Fermi surface bosonization in higher dimensions, specifically for the most part for this lecture, I'm going to restrict to 2 dimensions because that's where I can just easily draw diagrams and kind of explain things a bit more visually. But the thing I'm going to present is applicable in general for 3 dimensions as well, and higher D if you want, but this is a condensed matter school. 3 is the upper bound. So most of this is based on this paper by Luca Delacrita, who gave last week's hydro lectures, Ishan Du, myself, and my advisor, Dam San. This one paper and that developed this idea of higher dimensional bosonization from a sort of more geometric / mathematical physicsy approach, and how to capture interactions between electrons from this point of view using this bosonized technique. The other sort of more pedagogical reference would be my thesis, which is up on arXiv, if you want to take a look at it. There are a bunch of other references as well that I'm not going to write down, but they're all sort of cited in both of these. So I'll just sort of refer to those. Okay, so with that, we can get started. So what is the whole point of bosonization? This is the history behind this comes from studying sort of one-dimensional electronic materials, so like quantum wires or something like that, something with strong electronic correlations. The usual sort of perturbative expansion and interactions that y'all should have seen up over the last 3 weeks does not work in 1 dimensions because the perturbative expansion does not converge, it breaks down. So you need something different. So because of this, a bosonization technique was developed by various different groups, but generically this goes under the name of Luttinger liquids. This is big enough for the back to see, right? Okay. If it ever becomes smaller, just sort of yell out and let me know, and I'll return to this size. Okay, so what is the general philosophy behind bosonization? Step 1, you find a bosonic parametrization of the sort of an algebra of observables. So for example, in this case, it will be densities. Step 2, look for fermionic operators in this bosonic parametrization, the operators that can reproduce the fermion, the sort of electron operator that you can have, so that you can write that specific fundamental degree of freedom in terms of bosonic observables. Step 3 is to rewrite your Lagrangian or your Hamiltonian in terms of the bosonic operator. And then this basically gives you the bosonized theory that you can then work with. You have a dictionary for how to compare fermionic quantities with bosonic quantities. So if you want to calculate some correlation function or some observable of some fermionic object, you do that in the bosonic theory instead. So a lightning review of how this works. in 1 plus 1D is, let's say you have some wire with, say, for simplicity, a quadratic dispersion is epsilon k. Is k, there's some k squared over 2m star. And you fill it up at some mu or Fermi energy. So you're specifically interested in looking at low energy excitations in the system. This might be coming from just a single band in some material. So you're doing some sort of one band approximation so that you don't take into account interband hopping and stuff like that. So the sort of restriction to low energies means that at best, the only thing a fermion, a single electron can do, can sort of pluck itself out of the Fermi sea and put itself out here as an excitation. Note that because this dispersion is one directional, this is going to be a chiral excitation. It can only move rightwards. And on the other side, it can only move left. So you have a psi left over here and a psi right over here. Dagger for creation, sort of annihilation. And you can then write down what the charge density looks like, which is rho dagger R. So this is the normal order charge density. I am subtracting off the background. And then you can write down the Hamiltonian, at least for the free theory, in terms of this charge density, which is epsilon p plus bx times, b of p, Fourier transformed. And then you can also add interaction terms to this. The bosonic picture makes it clear what the sort of most important interactions are, the ones that are going to contribute at leading order in a momentum expansion. And these are forward scattering, which is, so the right, this should be plus. And backscattering. Is everyone here familiar with forward and backscattering and what they mean? If there's anyone, let me know. I'll explain it in the line. Yep. Oh, these are rows, the densities. Yeah, the sort of right chiral density and the left chiral density. Yeah, so forward scattering, just to recap, means that there's no momentum exchange happening at all between the two different fermions in the in state. So any scattering process that happens between two fermions here stays here, hence forward. And backscattering is the opposite. So there's a sort of large momentum exchange, the maximum possible happening. In the final states, there's no exchange, but if in some center of mass frame. But what happens is that the exchange momentum, the transferred momentum is large. All right. Yep. Between. Yeah, there in principle will be, you can kind of think of it as this with like one of the psi r, psi l sort of put into an expectation value. So I'm just being a little bit concise here in ignoring that. But yes, that's a good point. If you have some 2kF potential, then that will show up as well. It can also sort of present itself from this sort of term if V is localized on a 2kF density, because then the specific part of the density that matters is a right to left exchange. Exactly. Yeah, that's this.
Right and left goes to right, or right and left are interacting.
Yes.
What are this? Right goes to right, left goes to right, but they are interacting. Versus right goes to left.
So that's this. So you can drop, so let's say you drop the rho left term, for example, then that's a right forward scattering because it's rho right times rho right. So if you write this in terms of fermions, it'll be like psi right dagger, psi right dagger, psi right, which means 2 in states for right and 2 out states for right, Whereas if you write this in terms of the fermions, it'll be 2 lefts and 2 rights. Yeah. So it's up to some operator exchanging. Or
Like right goes to right, oh, okay.
Yeah.
Right goes to left.
yeah, so daggers are the in states, the non-daggers are the out states. Other questions? Yes, exactly, of the free fermions. So these are sort of ways to characterize interactions in a more organized way where you only take into account interactions that are marginal under RG. And here I'm not even talking about like BCS interactions, pairing interactions. There are other operators that you can define for that that'll come from like psi dagger, psi dagger. So this is right now is just the charge 0 sector. Question? This is all in momentum space, so you could expand it. So the coefficient of this, in principle, could be a series expansion in momentum exchange over PF. But any higher order terms are irrelevant. Yeah, so this is not, both of these are not strictly in the forward scattering regime, because these will be at like 4 different momenta. Forward scattering is when 2 of those become the same. And consequently, the other 2 also become the same. I'll talk about that a little bit more when I talk about 2D, when it becomes, where it'll be a lot more relevant to discuss those things. All right? Other questions? All right, awesome. So the way you do this, the way you do the bosonization, so this here Hamiltonian is in terms of fermionic observables. Interactions are uncontrolled. You can't do perturbative expansion, so you want to deal with it by bosonization. And the way you do that is you write down the algebra of commuting operators. So this is at x, and this is at x prime. And it gives 1 over 2 pi times delta prime of x minus x prime. X is our spatial coordinates here. All right. This thing over here is called a Schwinger term. And it corresponds to a sort of chiral anomaly, because particle number, as long as it's conserved, should commute with itself because it's a U1 charge. But its densities do not commute, and that is an anomaly. What that means is that if you couple it to some background gauge field, like an electromagnetic field, you'll see a consequence of that in terms of non-conservation of the particle number, just the right particle number. And from this picture, it's easy to see what that happens. If you turn on an electric field in, say, the plus x direction, particles, fermions from the left side of the Fermi sea will start moving to the right. So if you just look at the number of right chiral excitations, they will be increasing. And if you look at the number of left chiral excitations, they will be decreasing. And that's what this term is telling you. So for example, if you integrate this over x and x prime, then you get the number of right chiral particles still commutes with itself, which is what we should expect, given that this is a U1 charge. Okay, so this is the algebra that is important to us. And the question is, how do you realize this algebra using bosonic variables? So we'll do that by in the following way. Note that there's a derivative of the Dirac delta function. So if I sort of take the indefinite integral of the density, I'll get something that is conjugate to the charge density. So if I define phi such that this normal ordered rho r is dx phi, then phi of x comma rho r of x prime has canonical conjugation relations. Let me put a 2 pi over here. All right. And in particular, if I integrate this over x prime, what this means is that phi of x comma n is I. The number of particles has to be integer valued. So this means that phi shifts, phi is a charge one variable. It shifts by 1 times whatever your gauge transformation parameter is. Okay, so now you can, so because the Hamiltonian over there is only dependent on the density, you can immediately write down what the Hamiltonian looks like in terms of this phi variable. And you get the free Hamiltonian roughly looks like dx phi squared, because it's rho squared, with like whatever form factors here that account for the dispersion and the background potential, etc. And then you can sort of Fourier transform this to write down an action, which roughly looks like dx phi times dt phi plus v dx phi, where v is the gradient of the dispersion relation, the Fermi velocity, sometimes also written as Vf. Mhm. Oh, yes, sorry, there will be two different phi's. And then you can define phi equal to phi r plus phi l, and then there's another variable theta that is defined as phi r minus phi l. Yeah, thanks for pointing that out. So this is just for phi r. So this is what is called a chiral boson, because if you look at the equations of motion, you'll see that this chiral boson can only move to the right and not to the left. Oh, still use this. So going back to that procedure, we found a bosonic parametrization of the algebra of observables. And we kind of skipped this part. We didn't find fermionic operators. We already rewrote the Hamiltonian in terms of this bosonic operator. Yep. So it's because of this. The charge conjugate of phi, the canonical conjugate to phi should be dx phi, which is rho. Hence this cross term. That's what makes this a chiral action. Other questions? Just with this. Yeah. Yeah, this is a PQ dot term. Oh, I've just put all of that in these brackets. Like you can kind of work it through. It's basically once you know that rho r is 1 over 2 pi dx phi right, you just Fourier transform it and then plug it into the Hamiltonian. And it's a little bit subtle because the Neumann ordering matters. And that's how you sort of get to this. Mm-hmm. Not yet. This is just the right action. Yeah. But there'll be a corresponding left action as well. Exactly. Well, it doesn't matter. Yeah. So it'll be this plus then right squared. Sorry, a left squared. All right. Other questions? All right. So yeah, so notice that we kind of skipped step 2 over there and jumped straight to step 3. And the reason is because the Hamiltonian has to be a bosonic observable. So it has to be made out of bosonic operators. So in principle, you don't need to strictly find what the fermion looks like in terms of the bosons. You can kind of do a little bit of guesswork depending on how complex your system is in order to write down what the Hamiltonian is directly in terms of phi. But the fermion is still important to create other order parameters. Yes, question?
So in the picture, like your right and left, each side of their set of
Yeah.
but the definition psi are they're in space, right? Not in momentum, right?
Yes.
So like so when I go psi r of x and I go to momentum space,
Mhm.
it has component from both the parts of it, right?
No, because of the following. So the way you define these psi r and psi f is you have a total fermion, which is a psi dagger. And you, wait, can you see down here?
Yeah.
Can everyone see down here? All right. You write the total fermion as a Fourier transform, e to the I kf plus q dot x times psi dagger are, well, no, sorry, there's no q here, x plus e to the minus I kf dot x times psi left. So in that sense, what we're talking about here is that the sort of Fourier components of the psi right and psi left will have wavelengths, will have wave vectors much smaller than kf. So you're kind of splitting off the rapidly oscillating part coming from the kf, and you're just looking at the slowly varying part. Right. So in principle, if you want to exactly invert this, then you will have some components of psi L when you write psi R in terms of psi. But those components will be rapidly oscillating. So at sufficiently long wavelengths, you can just ignore them. So in this limit, they sort of decouple. OK, great. So at least in one-dimensional Bosonization, you can still do the second step, which is to find a fermionic operator. And this is what is called the vertex operator. So psi right dagger is given by the normal ordered exponent of e to the I phi right. And this is an object with charge 1 because of this commutation relation. Yeah.
I is the computation.
Yes.
I is the bosonic.
Yeah.
So that's the computation.
Good question. So that's a little bit subtle. There are different answers of different technical levels. One way to sort of make this work is to have what is called a Klein factor in front here, which is something you put in by hand, even though that's technically not correct. The more technically correct version, if you're familiar with like discrete global symmetries of theories, is that this is a duality between a fermionic theory and a bosonic theory. The fermionic theory has a fermion parity symmetry. So the duality is not strictly between the fermionic and bosonic theory. You have to gauge out the fermion parity first. And that's, roughly speaking, what this equation is doing. Right? Does that, hopefully that, I know that's a bit vague, but that's just the most technical version of the answer. But otherwise, you can do a Klein factor, put a Klein factor in front, which you say anti-commutes with itself to make this work. OK. Awesome. Yeah. Yeah.
The fermionic dispersion is 0 for me.
Oh, sorry, say that again.
We start out with a fermionic dispersion, which has a 0 at a Fermi vector, right? So then that gets absorbed, that gets shifted away by the theta kf.
Yes, exactly.
But there's still derivatives, which measure the deviation from
Yes.
that. So I guess one way to ask is, what are you writing as epsilon f(p)?
So here I've sort of assumed that it's simple and k squared over 2m, but you're right, higher derivative, higher order corrections, higher order nonlinearities in the dispersion do show up even in Luttinger liquids as like nonlinear terms. And
I'm not worrying about that. I mean, so you have minus the chemical potential, minus the Fermi energy to make it a.
oh yeah. Sorry, this would be like epsilon of p minus mu. Yeah.
But then strictly speaking, well, so there's always this subtle thing is, if you value it at kf, that will vanish.
Yes.
But then the corrections will not be, if that was a constant, then rho would immediately become d phi r squared.
Absolutely.
But instead, you have an additional derivative.
Yes. So that's what I mean by like non-linearities in the dispersion relation, because like if epsilon is quadratic, then it just truncates there. You just get this, and you don't have any higher order terms. But if you have higher order terms in epsilon, then you get higher and higher powers of phi.
But I mean, I'm asking, it seems like you don't get that. How do you get a constant times rho squared? That times rho. How do you get a constant time? Right, you have to point and split this rho.
Oh, yeah. There's definitely a lot of subtlety here. I'm just like not going into the details of that because that's not what I want to focus on for the lecture. Yes, yeah, absolutely. Yeah.
Do you have to linearize the dispersion at all, or are you keeping the quadratic?
So that's roughly speaking where this VF is coming. It's coming from the linearization of the dispersion.
Not actually keeping the quadratic part of the dispersion.
Yeah, sort of. So in principle, all of this will be corrected by order phi cubed, phi fourth, etc. And those corrections basically are determined by the higher order terms coming from the dispersion relation. Other questions? Oh, awesome. Okay, so this was the history of Luttinger liquids. A similar technique was applied in higher dimensions, specifically 2 dimensions as well, by sort of working out this algebra of charge densities. And I won't go into the details of that. I will just kind of mention the final results, and you can think of this as homework for the class. But what you can do is if you have, say, a 2D Fermi surface, you can define the analog of this chiral density as NP of Q, which is psi dagger P plus Q over 2 times psi P minus Q over 2. All right, so what this is doing, if you have this act on the Fermi surface state, which is a fully filled C, it creates a hole at P minus Q over 2 because of this psi, and it creates a particle at P plus Q over 2. So P is roughly the average momentum of these two. P minus Q over 2 is the total momentum of this. P plus Q over 2 is this. So the net momentum of this particle hole state will be Q. Okay, so it's creating a particle hole state, which is similar to what rho r of x is doing. If you Fourier transform rho r of x into psi dagger, it'll look similar to this, except this, instead of P plus Q over 2 and P minus Q over 2, it'll be psi r Q over 2, psi L Q minus Q over 2. Right. And you can calculate the commutation relation of these two, this operator with itself. And this is given by so it's some complicated looking expression. But this is only the leading part. This gets corrected by terms that are order Q over P. So already this looks much worse than this. Here, there weren't any higher order correction. The series expansion in momentum just truncates at this order, at the Schwinger term. But here, there are higher order corrections, so you can't really, and these corrections depend on this operator. You can already see that it depends on this operator and hat over here. They're not C numbers like in the left. So these are operator valued, so already they're not anomalies, and then there's even higher order corrections. But if you do an approximation and sort of replace this by the expectation value in the ground state, then it kind of looks like a Schwinger term. And then you just truncate this, then it kind of looks like a Schwinger term. A Schwinger term for each point on the Fermi surface. And then you can follow this exact procedure again and write down a sort of phi p of q such that how do I want to? So phi p of x such that gradient of x, gradient with respect to x in the unit radial direction is given by np of x, where x is the Fourier conjugate of this q. Right? And you write down an action which looks like this, except instead of this R index, you now have an index that labels every single point on the Fermi surface. So you have a chiral boson at every point on the Fermi surface, and you sort of integrate over that. So a more intuitive way of thinking about this is that you're taking this Fermi surface and splitting it up into radial parts, each of which is a Luttinger liquid. And then you're summing over these Luttinger liquids. Right?
So when you say tidal, what is the chirality direction? It's like a tangential to the
Yes, so the chirality will be this for each point. It's just,
radial.
yeah, radial. Same as over there, the Fermi surface is just a line, is 2 points. So the normal to that point is what the chirality is these two assumptions. So you're kind of doing an approximation where all of these patches are not interacting with each other, and you just have a bunch of independent Luttinger liquids. With keeping in mind that all of these Luttinger liquids sort of live on a cylinder. So you have a bunch of quantum wires living on a cylinder, and that's what this approximation is essentially giving you.
This theory is locally momentum.
Yes, so it'll be non-local in position space. Okay, so then the natural question to ask is, well, how do you account for all of these corrections and all of these corrections? Yeah. Yes, that is 0. Yeah. Yeah. So that's why it's a little bit weird. But so at this level, I'm not doing any low energy approximation. This is exact. This expansion is exact. Well, it may not be convergent, but still exact. But yeah, so that's why this makes sense at this level. It's only when you start thinking of this from a sort of low energy expansion point of view. Whenever you're doing a low energy expansion around a Fermi surface, the properties of the deep part of the Fermi sea should show into that expansion, and that shows up through here. Okay, fantastic. So I'll leave this as it is. So this is where the sort of Bosonisation procedure that my collaborators and I developed comes in. And the question that we want to solve is what do nonlinear corrections to this specific old school approach of Bosonisation look like? And unfortunately, in order to do that, we're going to forget about all of this. That's why I didn't take too much time in sort of presenting the details of it. And we're going to take a different approach. So this is called the coadjoint orbit method. Just a comment on terminology. This is a coadjoint orbit is a property of symmetry groups. For a Lie group, there's something called a coadjoint action. And the coadjoint orbit method applies whenever your space of states is related by the actions of some symmetry group. So if you have rigid bodies, all possible orientations of a rigid body are related by the action of rotation. So you can apply this method to write down a Hamiltonian or a Lagrangian formalism for a rigid body. Same goes for spin in a magnetic field. So the point of this exercise will be to show that the space of states for Fermi liquids, at least at low energy, are also related by the action of a Lie group, except that this Lie group is going to be an infinite dimensional one. So we start with the same thing here. We start with what algebra of observables are we interested in? And the algebra that I'm going to talk about are fermion bilinears. And just to be sort of a bit more explicit about this, I'm going to make this sort of Hermitian by subtracting the Hermitian conjugate of this. And then you can sort of Fourier transform this to between x and q, between y and p, where x, y, q, and p are defined up there. So X is so if you're looking at things in position space, this is a two-body operator. X is the center of mass of that operator, and Y is the relative distance between them. P is the sort of net momentum of this operator, the location of, in momentum space, the location of it, which should be roughly on the Fermi surface. Sorry, the average momentum. And Q is the net momentum of this two-body operator, right? And now you look at the commutation relation of this. So, oh, sorry, one more point. This is basically the same thing as what I defined over here. I just Hermitian conjugated it and sort of made it anti-Hermitian because of the overall I, just for simplicity. So you can then write down the commutator of these two. And the fun thing is that if you sort of look at that and work through it a bit more carefully, in the right space, which happens to be that of Q comma Y, this has a closed form. And it looks like the following. Bringing in the H bars again. So the left-hand side is one of these bilinears. The right-hand side is also one of these bilinears. The big difference is here I have not normal ordered. Sorry, this should have been the normal ordering. I have not normal ordered a priori, but we'll see that that can be accounted for later when I turn this into a Hamiltonian or an action. This method kind of deals with the required normal ordering automatically. Mm-hmm. No. Y is the Fourier conjugate to P. Y is position space. Q is still momentum space. Yeah. T is anti-Hermitian because of the I. Oh, you're right. Sorry. It's Hermitian. It's Hermitian. Yeah, sorry. In the thesis, I have an anti-Hermitian form, so I always get confused between the two, but this here is Hermitian. Probably. No, sorry. The minus sign is because fermion operators anti-commute. They don't commute. Yes. Because, so if you were to just take this and take its Hermitian conjugate, so ignore the I, just psi dagger psi. Its Hermitian conjugate would be psi dagger, which to bring it back would be minus. Maybe what?
If you take the dagger of that one, then get P minus Q over Q dagger.
Why is that?
Just take the dagger of psi dagger of plus Q. Then the daggers be not something.
Hang on. Oh, okay. So, right. I'm using a Fourier conjugate convention that is less common in condensed matter literature, where this does not, it should be minus P plus Q, this should be minus P plus Q. So this creates a particle at the opposite direction, on the opposite side. So in this convention, when you take the Hermitian conjugate, the location of the momentum does not change.
If I just think dagger comes to operator.
Uh-huh. So you have two different conventions, right? So you can do psi dagger x is integral e to the I qx. Let me call this k. Psi dagger k. But then you have a choice for how you take the Fourier transform of this, which is integral e plus or minus ikx psi of k. I'm choosing the one that's consistent with Hermitian conjugation not changing signs. So I'm choosing this one to be minus.
There's no create what's done yet. I think the point is that.
This is just how I'm defining psi of k.
I think saying like psi minus p plus q over two shows up in both terms in the t. And
Yeah.
psi dagger at the same momentum shows up. So if you just, in the second term, if I like undo the ordering, so I use psi dagger psi,
Mhm.
then it's just like.
Yeah, it adds. Yeah, that's right. It's supposed to add.
Okay, but then, okay.
Yeah.
Fine. I guess, why did you write it that way then?
Just because it was too complicated for me when I was working on this to keep track of like when the sign changes upon taking Hermitian conjugate, so I just didn't want to do that. So there's the convention I use.
It's already.
So what this means is that psi k dagger is psi dagger k.
That's always.
No, there's a lot of condensed matter literature uses the opposite convention where this picks up a minus sign. That's for sort of convenience with Fourier transform. Yeah. So there are two different conventions. This is the one I'm using. All right. Yeah.
Second term is just literally the same.
Up to a C number. Yes.
Where does this operate again? What?
Say that again.
You comment on the operator?
Yeah. It's just this particle hole creation operator. Yeah. The point of doing this subtraction is to sort of make sure that it's well behaved at large values of the momentum. Exactly. Otherwise, you'd get like a sort of, if you Fourier transform it into x and p at large values of x and p, it sort of goes to some non-zero number. Right. Yep.
Why?
No, y is the relative coordinate up there. x1 minus x2. Yes. So p is the average location of this particle hole. Center of mass in momentum space is not conjugate to center of mass in position space. It flips.
Isn't P here not a relative?
No, P is still K1 plus K2 over 2. So that's what this P is. All right, so psi does not create a hole at minus P plus Q over 2. It creates a hole at P minus Q over 2. All right, because of this Fourier conjugation. Again, these two conventions exist in the literature, and I know how confusing this is. I spent 6 months trying to decipher the differences. I promise you, if you sort of go back and think about it, it's all consistent and it does make sense. But these are the right signs. The fact that there are these two different conventions in the literature, nobody specified at the beginning of their paper, is very confusing. Yeah. Yes. Anti-Hermitian. Yes,
Writing in right?
exactly. That's all I'm doing. If this is confusing, ignore the I over 2, ignore the other thing. You'll
Ignore the other thing, the dagger of it, you get minus, you get psi dagger of minus P plus Q over 2.
yeah, plus some constant.
Right, so that's different than what you have. So it's not Hermitian.
Yeah, I see you're using the other Fourier transform.
Oh, wait, hang on. Sure. Whatever. It doesn't matter. It's just some science. But yeah, okay. So the fact that this algebra closes is important. Because what this means is that sort of take this and compare, for example, with the SU2 Lie algebra, the algebra of rotations. Lx, Ly is Lz. Ly, Lz is Lx, and Lz, Lx is Ly. So it's a very similar thing happening here in that these objects are forming generators of a Lie algebra. And just for completeness, let me just write the semi-classical phase space-like form of this, which looks like 2 over h bar, and then sine h bar over 2. So this is an infinite expansion in derivatives. You will recognize this thing as the usual Poisson bracket on a single particle phase space. But instead of just a single Poisson bracket, which would be if h bar was small, this is an infinite series in powers of the Poisson bracket being applied to this. All right? Yep.
Can I understand this as GMP algebra? Because
Yes and no. If X and P were one-dimensional, then this was GMP. But that's exactly right. In 1D, this is GMP algebra. Other questions? Okay. So in general, this is called the Moyal algebra. If you want to look more into this algebra in particular, I would recommend looking into like the history of in the old days when people were trying to figure out what exactly quantizing a theory means from a mathematical point of view. That's where this came up a lot, in particular in like Weil quantization of a single particle. But we're not going to care about that for now. For now, we just want to use the fact that this is a closed Lie algebra. So what do we do when we have a Lie algebra? We exponentiate it to create a finite transformation. So I'll first consider some generic linear combination, which I'll define as O hat f, given by integral over x and p, f of xp times t xp. So if these are generators, this is a linear combination. For example, compare with a vector being expanded in its components. That's what this is doing. And the commutation relation for O with itself, for two different O's coming from different component functions, is given by a third such O, whose component function is given by the Moyal bracket. So here the left and right arrows just mean this derivative acts on f. The right arrow means the derivative acts on p. Okay. So why have we done this? Well, it's because it allows us to conveniently create coherent states for excitations above the Fermi sea. All right. I'm going to redraw this. So the Fermi sea the ground state of the Fermi surface, at least for free fermions for simplicity, is given by a product of psi daggers acting within the Fermi surface on the vacuum. All right. So what this does is this fills up a Fermi C. Big diagram over here. This radius is PF, and everything within PF is filled. A single excitation on top of this would be to add a fermion on top, make it low energy so that it's close enough to the Fermi surface. But this changes the sort of charge eigenvalue of the state. So in order to compensate for that, I'll also add a hole somewhere here if I want to work in a charge neutral sector. All right. So this excitation is, if I once again label this as Q comma P, this excitation is created by psi dagger P plus Q over 2, psi minus P minus Q over 2, acting on the Fermi C. And I'll call this P comma Q. All right. So this is what a single excitation looks like. And you can then keep acting with more and more of these bilinears on top of this Fermi C to create more and more excitations. At least at this level, this is the same as T Q comma P acting on the Fermi C. Assuming that Q and P are oriented in such a way that P minus Q over 2 is within the Fermi C and P plus Q over 2 is outside, because then the other thing will kill the Fermi surface. All right, plus some C number term that's proportional to the Fermi surface. Okay, so if you have this, you can now create particle-hole coherent states. So let me define U phi, the operator, as exponent of integral over x comma p this operator, and then define the corresponding coherent state by phi, the function, as U phi acting on the Fermi C. So let's try and figure out what this means. So the first term in this the expansion of this exponential is just 1, so it's Fermi C. The second term is this, so it's a single particle hole state. The third term is the square of this object, so it's a state that contains 2 particle hole pairs, and so on and so forth. So if you compare with just simple harmonic oscillator, where you have coherent states defined by to the I, Z, A dagger, Z bar A, that's what this is doing. An A dagger would create a single level. Z is sort of a form factor for it. And then higher and higher order terms would create multi-level states, and it's an infinite linear combination of these. So this creates a coherent state of particle hole pairs on the Fermi surface. So for a single particle hole, you can sort of think of this as a small Fermi surface deformation, where you're sort of dipping this in a little bit and dipping this out. And the point is that in a semi-classical limit, this coherent state is literally a shape deformation of the Fermi surface. Now, so let's show that. Here. Oh, and since I forgot to mention, so that was the point of creating those O hat Fs. This thing is basically O hat phi in the exponent. And so this is literally an exponentiation of that Lie algebra, which means that this is a group element. Um, so in order to show that, get a physical interpretation of what this coherent state is, specifically as a shape deformation of the Fermi surface, let me define the sort of occupation number function. This is going to be half plus the state phi times txp, the expectation value of this bilinear object in the state phi. And the reason for this half is because we sort of, well, I erased it, but we sort of anti-symmetrized the fermion bilinear, right? And if you work this out, this is basically given by, okay, so before that, let me define the ground state distribution function, which is the same thing, but in the Fermi sea. So for a spherical Fermi surface, you can show that this is given by a theta function, Pf minus mod P. So it's 1 when you're inside the Fermi surface and 0 when you're outside. This is literally the sort of Fermi-Dirac distribution function at 0 temperature. And then f phi then takes, upon expanding this u, an infinite series form in terms of nested Moyal brackets. I'm putting a factorial explicitly here just so that y'all can see what the other terms will be like. So the 3 bracket term will be 1/3 factorial and so on and so forth. Now let's take a semi-classical limit here. So recall from like the 1D discussion that we're only interested in sort of low energy excitations of a Fermi sea. In particular, those low energy excitations mean that this net momentum has to be much smaller than the Fermi momentum. And this average has to live close to the Fermi sea. All right. So for low energies, we need Q much less than P, much less than PF. Okay. Sure. Yeah, you can add a normalization factor. Oh no, here I'm not assuming a normalization. Okay. Yeah, this is just well, I mean, this is an anti-Hermitian operator, so this is a unitary operator, and this is normalized. Well, this is normalized, so you don't really have to do any extra normalization. All right. So what does this mean in position space? It means that the conjugates grad x dot grad p acting on anything, so is much less than that thing itself. So the dot product of x times x and p gradients of a function of x and p is much smaller than the function. Yes. Oh, whoops, sorry. Thanks. Yeah, p has to be of order pf. Oh, yes, sorry. This is much less than the function. So another way of writing this is that grad x dot grad p is much less than 1. All right. So what happens in this semi-classical limit? Let's look at this Moyal bracket. The argument of the sign is much smaller than 1, so you can linearize it. H bar over 2 cancels with the 2 over h bar. So this Moyal bracket of 2 functions becomes a Poisson bracket. All right. Okay. And I will mention, without spending too much time emphasizing why, that this algebra of functions on a single particle phase space with the Poisson bracket is the Lie algebra of canonical transformations of the phase space. So canonical transformations are those coordinate transformations of x and p that preserve the Poisson bracket. And you can show that these are generated by functions of x and p such that two such transformations, the commutator of two such transformations is generated by the Poisson bracket of f and g. Okay. So what do canonical transformations do in particular? They obey Liouville's theorem, which is that they preserve phase space volumes. So if I have this f phi, which is related to f naught in the semi-classical limit by a sequence of Poisson brackets, what this is doing is starting with a circular Fermi surface, and then acting on it via a canonical transformation generated by phi. And canonical transformations, because they have to preserve volume, they can't change the fact that f naught is 1 within a closed surface and 0 outside. They're continuous deformations. So all it does is gives you some different shape within which f phi is equal to 1, and then f phi is 0 outside. To see this algebraically, notice that phi comma f naught, because you have a grad p acting on f naught being the theta function, is proportional to delta of mod p minus pf. And then two such Poisson brackets acting on f naught is proportional to delta prime mod p minus pf, and so on and so forth. You'll get higher and higher derivatives of delta function. So this series, including the factorials and the other coefficients in terms of gradients of phi that show up, organizes itself as a Taylor expansion. And if you resum that Taylor expansion, you'll find that f phi is theta function of some pf tilde minus mod b, where this pf tilde depends on phi. Yeah. We're not doing angular harmonics yet. Yeah, because we've not done any expansion in L's. So this phi here depends on x and then vector p, which means mod p and theta. So it's still, theta is still here. We've not Fourier transformed this yet. Yeah. So, sorry, can you say that again? Yeah, x and p are like a single particle phase space. But the phase space, so what I'm saying is that the phase space of Fermi liquids is this orbit of states related by canonical transformations. All right. Does that make sense? Because you can generate any such space, any such state from the ground state via a canonical transformation. So if you have two different such states, f phi and f phi prime, then you can undo the canonical transformation on the first and then do the second one to relate those two. The semi-classical approximation there. That's just the fact that it's Poisson brackets instead of Moyal brackets. Yeah, that's the approximation. So at the level of Moyal brackets, these generic states will not have sharp Fermi surfaces. They'll be fuzzy. But in the semi-classical limit, they become sharp.
So phi is the function that maps to the
Exactly. Exactly. And in fact, so phi isn't unique. So if I give you some shape, there's not just one phi that'll achieve this transformation from a spherical Fermi surface to this shape. There are multiple possible phis because there can be canonical transformations that leave the spherical Fermi series invariant. So you can always compose u phi with such a canonical transformation to get something else. Yes. Yeah. So you can use that freedom to sort of kill this mod p dependence on phi. So said more precisely, what that means is that this more precisely, what that means is that the space of states, the space of low energy semi-classical states of a Fermi surface, of a Fermi liquid, is not just the full group of canonical transformations, it's some coset of it. So suppose I define H as the group of such U alphas in the semi-classical limit such that U alpha acting on the Fermi C leaves it invariant. This is a group. And G is the group of all canonical transformations. Then the phase space for Fermi liquids is given by the coset G mod H. So, and a typical element of this is a canonical transformation up to identification by a shift with H. Right? Yeah. 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 There will be some stuff that some derivatives of phi on the right-hand side. Exactly. Specifically for the first line, it will be minus p hat dot rad x phi. Yeah. All right. No, it's not. LU1, okay, so LU1 is only a symmetry of the strict fixed point of Fermi liquids. Nonlinear corrections break LU1. But there's still a question, I would say, of to what extent can LU1 be used to still constrain some of the nonlinear relations. In particular, the operators that break LU1, the irrelevant operators that break LU1 that do contribute to nonlinear transport, there might be some nonlinear quantity that does not depend on them. And in that case, LU1 could still help fix those. But in general, LU1 does not work for nonlinear transport. And nonlinear transport is important even at the fixed point because if you're strictly working at the fixed point of a Fermi liquid, you cannot get a density 3-point function, for example. The density 3-point function would vanish at the fixed point. So you do need to account for these nonlinear corrections. Question? This is not a symmetry group. It's the same as saying that if you have a maximally anisotropic rigid body, then rotation is not a symmetry group. Exactly. It's just that this manifold of low energy excitations is controlled by this group action. Well, you can have like the manifold is a coset, but the action of the group on that coset still exists to sort of change spaces. Exactly. And the reason you have to mod out is because the ground state is what breaks. The ground state is not invariant under the full group. So I would say that this is a symmetry. or rather a redundancy because it preserves the ground state. So in some ways you can think of this as spontaneous symmetry breaking, even though the space of canonical transformations wasn't a symmetry to begin with. But if you start from a vacuum theory, so no fermions at all, then you have in principle a canonical transformation symmetry of the vacuum. But you turn on a chemical potential and suddenly that gets reduced to H. Right. So in that sense, you can sort of phrase it as spontaneous symmetry breaking, but it's kind of not because canonical transformations wasn't a symmetry to begin with. Yep. In the what case? It's a good question. There's still, I can't really say because I don't know how to compare the dimensions of infinite dimensional Lie groups. But if anything, I would say it's probably smaller because generally, so the Moyal situation should be obtained from this semi-classical business by quantizing. And whenever you quantize, you reduce because you kill away things that are classically possible, but quantum mechanically not possible. Like a classical phase space is X and P. A quantum phase space, wave functions only depend on X. But yeah, so in that case, I would argue that it has to be smaller. Other questions? Yep. Sorry, say that again. Yes, but because of this modding, you can make it just depend on X and theta. The theta being the angle in phase in momentum space. Yeah. It locally changes the shape of the Fermi surface. So at every X, you'll have a different profile. Yeah. All right. Awesome. Yeah. Probably, yeah. You could think of this as a non-commutative field theory in like X and P space. That's where the Moyal bracket comes in. So I haven't thought about it too much, but there might be some like sort of finite matrix model type regularizations of the Moyal bracket or something like that. Actually, Sihan next to you probably knows more about this. But yeah, the reduction in dimension, the reason I'm saying that is because if you were, there's piece of technology in mathematical physics called geometric quantization. And this is sort of the first half of geometric quantization of a theory. And if you were to follow through with the second half, you would get the Moyal stuff back again upon the semi-classical. If you like geometrically quantize the semi-classical theory, you would get the Moyal stuff back. And in geometric quantization, you usually have this reduction of phase space happening. Because you always have to kill the like momentum variables out of the phase space for the wave functions to depend on. All right. Okay. Yeah, yeah. So in 1D, yeah. Here you have a symplectic form. In phase space, there's a symplectic form which acts like a magnetic field would in real space. So if X is one, X and P are both one-dimensional, you can think of P as Y instead. And the magnetic field becomes the symplectic form in this case. All right.
You always work beyond Moyal product, right? Sorry, you're always working in the approximation that Moyal product is just.
Yes, yeah. At least for these references. Yeah, we're definitely working in this limit where Moyal is semi-classical. There have been some like papers where more recently by Yushuan and Mengxing, where they use the full power of the Moyal bracket in the presence of a magnetic field, because there it simplifies it a lot, because it kind of factorizes the center of mass coordinates. You can kind of either the center of mass or relative coordinates. One of those you can sort of just get rid of and focus on only the others, and it becomes much simpler to work with. Okay. All right, so now that we have, so just as I predicted, we're not going to need most of the right-hand side of that. So don't worry about that notation. So let me show you the quick and dirty route to getting the action / Hamiltonian out of this this Bosonisation approach. Yep.
The forward join orbit nature of this, but
Yeah. Right. So
I mean, when is it always some action?
yes. So the point is that every state is related by a group transformation. I mean, even if there's just some like orbit of some theory, it still works. But it's just that this Berry phase term that I'm about to present might look slightly different from a global point of view. When it's a coadjoint orbit, there's a natural sort of symplectic form that you can write down on the orbit itself. On other orbits, it might be a bit more involved.
But it's always, Berry phase is always overlap between two
Yes.
years.
Yeah.
State.
So if you have some ground state to expand around, you can always write down a Berry phase term, but that will still be local. So for example, take a spin in a magnetic field. Let's say it's starting at Z. At Z. You can always write down a Berry phase for small fluctuations, but that Berry phase term then doesn't tell you that there's a sort of compact space. So in order to get the compact space, you need a symplectic form. So here because all of this is sort of expanding around the ground state to begin with, even in the semi-classical limit, I don't know about this like topological global data. But yes, so I'm just going to present the Berry phase approach to it. Yeah.
Semi-classical picture, what is coadjoint orbiting?
Okay, so it means that this F naught is a reference state. You act on it with all possible canonical transformations. The action that I wrote down is called the coadjoint action of canonical transformations, because it's, if you think of Poisson bracket as commutator, it's like 1 plus commutator plus nested commutator and so on and so forth. Hence co-adjoint action. Well, hence adjoint action, but co because reasons you can look into my thesis for. Because technically this is an element of the dual space and not the Lie algebra. But don't worry about that too much. So that's what makes this a coadjoint orbit. It's the space of all states that you obtain by the action of all group transformations from some reference state. Okay, so the lightning derivation of the action. So let's say we have some generic time-dependent trajectory in the space of states, which is, as always, exponent integral xp phi of t acting on the Fermi C. Then this gives a Berry connection on the space of states, which is defined by curly A and I will leave this as an exercise to show that in the semi-classical limit, this becomes the following. Dots are confusing on board, so I'm just going to rewrite this as explicit DTs. So this is what this looks like as an expansion in phis. Okay, a series of nested Poisson brackets of phis with dt phi. I want to emphasize here that this is not the same as that expansion, because if you look closely, the numerical factors are at different locations. So this comes from u inverse dt u, where u is e to the phi. In sort of, if these were matrices, this is what this would be, right?
non-cojoint
Mhm.
excitation. Just like creating bubble of fermion, the bubble Fermi CEO creating some high energy excitation. like
Yes.
where You have like a large hole.
Yeah,
And
exactly.
That's described by.
Exactly.
Canonical triangle.
Exactly. Although Moyal transformations might be able to describe them, because Moyal is just proliferating particle hole pairs everywhere. The semi-classical limit, you sort of force them to be close to the Fermi surface.
But when you say cojoint orbit, that is already semi-classical limit.
So you can have a cojoint orbit for the Moyal group as well.
Okay.
Yeah. It's just really hard to work with, except like in the case of the magnetic field that Yushuan and Mengxing did in their papers. So yeah, it's something I have not tackled yet. Yeah, so whenever you have like some adiabatically changing Fermi surface, so you're slowly populating particle hole excitations. I mean, assuming you're just doing it slowly, for example. Like let's say you're changing the background potential slightly, so F naught of P becomes now X dependent or slowly, or something like that. When what? Sure, yeah. But the point of the Berry phase term, besides like being applicable to adiabatic change ground state, is also that it helps you write down an action. What the Berry phase term really means is that your theory is chiral, so that the complex the canonical conjugate of your degree of freedom is the degree of freedom itself, or some other modes of the degree of freedom. And the Berry phase term helps you write down how exactly to turn this into an action. So the action as a function of phi is then given by integral over dt of the Berry phase term minus some integral over dt of some Hamiltonian that I've not yet specified. So this is what that means. If you don't have rapidly oscillating things, so no Hamiltonian, then the Berry phase term controls slow changes. But then if you have rapidly oscillating things, then it's Berry phase plus Hamiltonian stuff. Right? And then you can take a semi-classical limit of this. So we have this. What we need is this. And this is where this sort of going back to this picture of looking for fermionic operators versus really writing down the Hamiltonian directly in terms of the bosonic operators comes in. As of yet, I do not know how to write down a fermionic operator in this sort of higher dimensional bosonization theory. There are some suggestions, there are some proposals. I just don't know which of them is correct, and I don't know how to test them yet. So instead of sort of finding the right fermionic operator, what we're going to do is just kind of write down from intuition, from sort of educated guesswork, what the Hamiltonian would look like. So for the Hamiltonian, we do two things. The Hamiltonian should only depend on phi through f of phi, because if two different phi's create the same state, then they should not lead to the different Hamiltonian. Secondly, I'm going to expand in nonlinearities. So sorry, not nonlinearities. Expand in fluctuations around the ground state, because I'm only interested in low energy observables. And then I'm going to take a semi-classical limit because that corresponds to low energy. To allow myself to do a gradient expansion in grad x over pf. So again, what this means is that I'm only looking at excitations that are close to the Fermi surface. Yeah, I'll just write down the Hamiltonian, and that should be more or less it. the last 5 minutes I'm going to spend on like interpreting what terms in this Hamiltonian. So with those three principles, the first one of which is exact, and the second two are approximations. The second and third are approximations. I'll write down the most general Hamiltonian. Notice that I'm making X local because of the third expansion here, which allows me to do a derivative expansion around some local theory. Plus a bunch of infinitely many terms. So this expansion, as I mentioned, is organized in number one, fluctuations. So this is a linear in fluctuations term. These two are quadratic in fluctuations. This is cubic in fluctuations and so forth. And then secondly, gradients. So both of these are local. This is first order in gradients. This is local. And then there'll be more higher gradient terms at every level. So what do all of these functions that go over here are, they're called Wilsonian interactions or Wilson coefficients or Wilson parameters in an effective field theory, which means that they are arbitrary functions put in by hand to be compared with experiments to figure out what they specifically are. This is a way to just organize any sort of sequence of interactions, any set of interactions that you might have in a low energy theory in order of how important they are for any specific thing that you want to calculate. This can then be further expanded into an expansion in phi that unfortunately I don't have time for, so I will cite the references. And you can then do proper full-scale RG on this, try to figure out the relevance and irrelevance of specific terms. You can do power count, figure out how any given correlation function scales with momentum, etc. But specifically, let's look at this one in particular. Delta F is roughly psi dagger psi. Okay, so a delta F squared term is a quartic interaction to some order. Yeah. Yes, I'm just getting to that. Yeah. So this is roughly a quartic interaction. And once you work out the details by looking at sort of maybe Fourier transforming, because this becomes Q, this becomes minus Q over 2. So Q over 2 and minus Q over 2. When you Fourier transform and you sort of look at the specific labels for this, you will find that F2, 0 at values Pf of theta and Pf of theta prime. So when placed on 2 points on the Fermi surface, is the usual Landau parameters of Fermi liquids. But there's also like here, we've not required that these be restricted to the Fermi surface. There are higher order corrections in here. There are higher order corrections to this term. There are higher order corrections through this. So this is a way to systematically account in a fluctuation and gradient expansion, all of the non-forward, non-marginal interactions that are important in Fermi liquid theory. The reason they're important is while Landau interactions are obviously the most leading marginal parts, these sub-leading terms will show up in nonlinear transport properties, for example, the density 3-point function, the current, at the same sort of order of contribution as the Landau parameters times whatever powers of momentum that you have. So if you want to fully systematically account for all of the consequences of nonlinearities, all of the consequences of irrelevant corrections, you need to keep track of all of these in this expansion in phi. Right. And so this action, that S expanded in phi minus the Hamiltonian expanded in phi, basically gives you a systematic way to account for all of these interactions, at least for small momentum exchange processes. And presumably there are ways to do that for larger momentum exchanges by sort of expanding this algebra of fermion bilinears. I have thoughts about how to do that for superconductors by expanding the algebra, and there's more to be explored here. Thank you. Questions? Yeah. Yeah, you go. No, it's now local because of the gradient expansion. Yeah. So the idea is that all of the non-localities have been absorbed into this sort of these coefficients. So in X and P space, it's non-local. But in X space, it's still strictly local because this is both X, these are all X, these are all X. And it's the semi-classical limit that allows us to do that. Yes. Yeah. Under these canonical transformations. Yes. Yes. Yes and no. So if you wanna account for superconductivity in this, you have to expand your algebra because here I started with just charge 0 fermion bilinears. You also need to add to that psi dagger, and psi. And those still the set of these three still form a closed algebra. So you can none of us have done this in practice yet, but you can in principle expand this whole algebra to have, instead of just the f phi, you can have like f plus 2 and f minus 2 sort of distribution function versions of the order parameter, superconducting order parameter as well. And then like in the same way as we compute the Fermi surface ground state, you could compute the BCS ground state in that sense, see what the distribution function for that looks like, see what its stabilizer is, and get a different kind of H. So it's not like you're breaking H down, you have a larger algebra to worry about. Yep. No, they can't. Because they're strictly semi-classical. If you go back to the sort of Moyal picture, they could in principle change the Fermi surface topology, but it's not particularly controlled, unfortunately. There was a question here. If you restrict it to, so this is not just one sort of RG covariant interaction. It's a set of infinitely many, as you get from like first restricting to the Fermi surface or taking its radial momentum derivative and restricting that to the Fermi surface, or higher and higher derivatives. So the restriction of that to the Fermi surface is exactly marginal, up to loop corrections.
Higher radial derivatives will be irrelevant.
Yes.
So this is consistent with like Shankar.
Exactly. You can reproduce Shankar-Polchinski out of this. Question? Yeah.
Right. So I mean, U is this operator that creates a coherent state of that particle excitation.
Yeah.
So I'm thinking that what examples are there to that it does not change information, that what are members of H group?
A global rotation. Like just any global symmetry transformation you can embed into canonical transformations. In terms of this phi, so for example, you can think of phi equals, I believe it's x cross p is what performs a global rotation. So it leaves the ground state invariant. But there are many others. There are in principle functions that you can construct sort of order by order in some expansion that will just leave the Fermi surface invariant. Yeah, other questions? Yep. Great question. No, specifically because of this. Backscattering is a 2kf. Okay, so there's a slight terminology overlap here. You can have Landau parameters that correspond to some form of backscattering. Specifically, if you have, like in this theta context, if the difference between theta and theta prime is pi, then that's backscattering. So that is included. But 2kf physics is not, because, so let me draw a Fermi surface real quick. Backscattering can be thought of in two different ways. If you have a particle hole pair like this, and another one like this, and any such configuration with initial and final, then this is not included because there's no limit you can take where the particle hole pairs have small momentum. But the part of backscattering that is accounted for by this is this sort of configuration, where if you can think of these as particle hole pairs, or you can think of these as particle hole pairs. Because this gradient expansion means that you need this to be much smaller than this. Yep.
Replaces the canonical transformations for the super.
It'll be a larger group. I don't know if there's a name for it. Sort of, yeah. Well, not quite, because the algebra of T2 with T minus 2 is different. It's not a direct product. There's some different parts of the algebra, because you have like three types of generators then, which is like T plus minus 2, and then T0, which is what the ones we were working with, and then yes. So these would be like psi dagger, or psi. But yeah, so like T2 comma T minus 2 would be T0, and T plus minus 2 comma T0. Yeah. Oh yeah. In terms of like, this particular form, it's similar to SL2R, but it's not a sort of direct product. Yep. So if you work out, so the fact that there's a Berry phase term makes it chiral. So when I say chiral, I mean that there's a linear and time derivative term in the theory. In the spatial interpretation, it just means that if you sort of expand this in phi and take the leading order part, you get the like one Luttinger liquid at every point. That's the quadratic truncation of the action.
Physically, just at every point of Fermi surface.
Exactly.
In that direction.
Yeah. Exactly. Exactly.
1D, there's a slope there.
Exactly. Yeah. But like this also gives like all potential semi-classical fluctuation expansion corrections to that, coming from nonlinearities, curvature of the Fermi surface, etc. Yeah.
In this infinitely many Luttinger liquids where there's presumably a consistent theory where the Luttinger fraction is a non-trivial. Does that have an analog?
Not that I know of, because that would still sort of be almost quadratic. Like this Berry phase term, you can never truncate it. It does not truncate at quadratic order, except for like very specific case of Fermi surface shapes. So even if you have like infinitely many Luttinger liquids with some like flavor-dependent Luttinger parameter configuration, you could still not get the effect of curvature. Here, I don't know. Here, I genuinely don't know. Like, because I don't even know what the fermion operator is in this theory. But I will say that one way to think about it is if you take the set of all charge neutral bosonic operators in Fermi liquid theory, then that sector is equivalently parameterized by this in the semi-classical limit. I'm not sure. For free fermions, there's this paper by Takamori Park and Leon Balins, where they do that by sort of doing a Legendre transformation, but for bilocal sources of the path integral. But for interactions, it's not quite clear how to do that. Yeah. Yep. So that's not my work. So I would highly recommend looking at this paper by Yushuan Wang. They have 2 papers. But the basic idea is that if you look at the specific form of the Moyal bracket in this magnetic field, you don't just get this sort of where do I write this? You don't just get like grad x dot grad p minus anti-symmetrized. You also get something that is proportional to b grad p dot grad p. And now if you work in sort of center of mass and relative coordinates, like specifically in the context of a magnetic field, this can factorize. So you can ignore some sort of global center of mass dependence or something like that and only focus on the relative coordinates. I don't remember which one you can ignore and which one you can't. But that makes this sort of doubly infinite dimensional thing much simpler to deal with.